All right. So what we're doing today is we're gonna ease into the next section, which is dealing with solubility, functional groups, intermolecular forces. But we're gonna probably cover the functional group and intermolecular forces stuff between Monday and Wednesday. Since the exam is on Blackboard, we're gonna still have class on Wednesday. We're not gonna like not have class to take the test. So what I'm gonna do over the weekend, I'm gonna send you some videos on functional groups. Those are videos that I made very early on in this process of doing like a flipped classroom. So please excuse the poor drawings. I haven't had a chance to go back and update those yet. But the information is what it is. But the drawings and stuff are not so great. I was using like a bamboo pad, all this stuff. So anyway, those are kind of, I don't want to say brutal, but they're not as good as some of the later videos. So just be patient, bear with that. And I'm also going to send you some information on solubility, send you a video on that, and also a video on intermolecular forces. All right, so that's a lot of information, but the functional group stuff, again, is all memorization. And then the solubility and the intermolecular force stuff is not that bad. It's just when we start talking about it, you'll see it'll make a lot more sense. All right, so do me that favor this weekend. Take some time. It might take you like maybe 1 hour to go through everything. Take notes, pause, rewind, all that stuff. Write down questions if you have questions. And then on Monday, we're going to hit those topics. Between Monday and Wednesday, we're going to hit them hard. And then we'll take the test Wednesday and just keep pushing. All right, so today we're going to do a quick review on formal charge because that's an important concept. Was there a question? Okay, so we're going to do a quick review on formal charge. We'll keep talking about dipoles and how dipoles and polarity affect solubility. I'm going to introduce you to that. And then we're going to hit resonance today pretty hard. And for the rest of the time, that's what we'll be doing. All right, so let's jump in right here on this sheet 1.13. And let's do I, H, B, and A and F. All right. And this is, again, we've already talked about formal charge. This is just refreshing because when we do resonance, you're going to see some structures have negative charges. Some might have it might be a cation, it might be an anion. So I don't want you to have to spend time wondering why it's positive or negative when you can look at it and determine what the formal charge is supposed to be. All right. So let's do A. And how do we determine formal charge again? What's the little formula we use? Anybody?
Valence minus actual.
Valence minus actual, right, is formal charge. So the valence of aluminum is what? What group is aluminum on the periodic table? It's 3. And then what is the actual for this molecule right here? How many electrons does aluminum have around it here? It's 1 from each bond, right?
4.
Yes, so 3 minus 4. Sorry about that. So the formal charge of this molecule is what? -1. So we'll put a negative sign near that atom. Yes, no?
Yes.
All right. Let's do B real quick. What's the valence for oxygen? If it helps, you can download a periodic table and just keep it in your phone or your device, or stick one on your desk somewhere. Go ahead.
8? No.
No, the valence for oxygen is, let me see, somebody might have put it in the chat. 6, good. Hayward, thank you. The valence for oxygen is 6. And then how many does it have around it? 1 from each bond. So that's 1, 2, 3.
5.
And then the lone pair makes 5. Very good. So 6, keep trying to write with the highlight. 6 minus 5 is +1. So we put a plus charge next to oxygen. Are y'all following that?
Yes.
All right. What about F? We should be able to do that without any calculations. Carbon has 3 bonds to it, and it doesn't have a lone pair, and it doesn't have the 4th bond. What do you think?
+1.
+1. Good. Excellent. But just for the sake of clarity, carbon is 4. Valence is 4. Actual is 3. So the charge is +1. You can see it has 1, 2, 3 electrons around it. All right. Any questions on that? All right. Let me add one. Let's do G as well, because that has multiple atoms. Let's do all 3 atoms. What about this? Do we have to do that? Doesn't it have 4 bonds already in the 4 octet?
Yeah.
So what's the charge on it?
0.
0, right? It's not charged. What about this carbon? Can we say the same thing for that one?
Yes.
Yeah.
Yeah, charge is 0. What about oxygen? Right, you see the lone pair, that's 2 electrons. And then it's in a triple bond with carbon. So that's gonna be 1 electron from each one of those bonds. So 3, 4, 5. So valence is what? For oxygen, 6. Actual, 5. Charge is +1. Is that right?
Yes.
All right, great. All right, let's do H. We're gonna do, if you look at the chlorines around aluminum, these chlorines here, here, and here, what would the formal charge for each one of those be? All right, it's got a 4 octet. It's got 7 electrons around it, and the valence is 7.
Yeah.
0 for all of them, so we don't have to calculate that. What about aluminum?
-1.
-1, very good. Right, that's valence is 3, actual is 4, so the charge is -1. Anybody not see that, how the actual is 4?
I don't.
Okay, how many bonds does it have around it? The aluminum.
4.
Okay, and each one of those bonds is contributing 1 electron to aluminum when we're trying to calculate the charge. So the actual in this case is you got 1 electron coming from here, 1 from here, 1 from here, and 1 from here. So the actual is 4. Valence is 3 based on the periodic table.
Oh, okay. Thank you.
All right, what about the other chlorine? Let's do that one. The one here. What's the valence for chlorine? It's group what?
7.
Group 7. Good. Speak up. Be confident in your answers. All right, group 7. So valence is 7. And it, as a rule of thumb, and the reason why I picked the other chlorines is because it's understood that chlorine can only form, well, let me think, not say only form, chlorine in its most basic, like natural state, is only gonna have 1 bond to it, to another atom. So when you see a chlorine that has more than 1 bond to it, then that's kind of, I don't want to say a red flag, but we gotta figure out what the charge is if it has more than 1 bond to it. If it only has 1 bond to it, then there's no need to calculate it because it's understood that chlorine is neutral, right? So 7 is the valence. And then how many does it have around it?
6.
6, very good. right? You got 1, 2 here. You got 2 lone pairs, so that's a total of 6. So 7 minus 6 is +1. So that chlorine is positive. Just like that aluminum is negative. All right. And then the other chlorine, you can see it's going to be 0. Because it's just like the ones that I have highlighted in yellow. 1 bond, 3 lone pairs. So it's the charge on that is going to be 0. All right. Let me ask a question.
So would 0 also be kind of like plus or minus, like being neutral, like plus and minus, or is that like?
No. It's just neutral. Because when you add up the valence and the actual, you're not gonna get you're just gonna get 0.
Okay.
Yeah. Great question. All right. What's the overall charge on this molecule? If everything is 0, except for that 1 chlorine, which is +1, and the aluminum, which is -1, what's the overall charge?
0.
0.
Bro,
Because the chlorine and the aluminum are going to negate one another, right? That's important because when we start talking about resonance, the overall charge matters. Like it has to stay consistent throughout the process of resonance. So I'm just throwing that at you now, so you'll have it in your back pocket when we see it again. So I'm gonna write that right here. Zero. All right, we got one more to do. Let's do that one. And let me throw some functional group nomenclature in at you too, because again, functional groups that's something once we dive in, we can't come out of that pool. We're gonna be in that pool for the rest of the semester. So right here, you have a nitrogen that is bonded to 3 hydrogens. And then you have a 4th bond over here to carbon. Let's calculate the formal charge, and then I'll tell you what that functional group is and what some derivatives are. All right. So what do you think? Nitrogen is 5. Is that right? Valence is 5. And then the actual will be what?
4.
4. Good. So the charge on that is positive. When you have a positively charged nitrogen like that with all sigma bonds, we call that, and let me write it over here, we call it an ammonium. Right? It's a nitrogen. Let me back up. All right, let me move this. So it's a positive. That's what this little shorthand is. Plus and an apostrophe and VE is a shorthand for positive. Right, so it's a positive nitrogen with all sigma bonds to it. We'll call that an ammonium. If it was a nitrogen, like a NH2, right? So it had 3 bonds to it, no charge, lone pair. We call this an amine. Right, so nitrogen can have it can have other derivatives. The ammonium is actually a derivative of the amine. And then if that nitrogen is connected to a carbonyl, a C double bond O, which we're going to talk about, so don't panic if you know the terminology sounds weird. So if that nitrogen is connected to a carbonyl like that, it's called an amide. I can fit it in here, IDE. So the amine, let me box that in or something, or move it. And I'm going to put an R group out here. And nitrogen in its normal state, 3 bonds and a lone pair. Like in the lowest energy state, that's how nitrogen exists. Has 3 bonds to it and a lone pair. All right. So amide is if that nitrogen is connected to a carbonyl. I knew that was going to happen. And then amine is if it's neutral and just all 3 sigma bonds in that lone pair. And then ammonium is a positively charged nitrogen with all sigma bonds. All right, so I'm just I'm sliding in the functional group stuff where I see it so that some of it won't catch you by surprise when I send you those videos. Some of it you'll already know. All right. I like doing that because what it does is it, instead of me just pausing and just going functional group by functional group, it's much easier to pick them out as we see it. All right, let's go to the carbon. What is the charge on carbon?
0.
0.
0, right? Right. And then the hydrogens, they only have a charge if they're not connected to anything, right? So hydrogen, let me give you a little piece of information on that. If you have a hydrogen, if it's by itself with no electrons, we call it a proton. If it has a pair of electrons and a negative charge, we call it a hydride. And those are special cases, right? But if you just see hydrogen in a molecule bonded to something, 9 times out of 9, it's going to be neutral. So we don't worry about calculating formal charge on hydrogen unless it's one of these 2 special cases. A proton being a hydrogen with no electrons, and then a hydride being a hydrogen with a pair of electrons. It'll have a negative charge. Right, but those are, again, are special cases for hydrogen. Right, under normal circumstances, we don't even bother worrying about hydrogen because we know it's going to be neutral. All right, let's go to the next atom. Here, this carbon, what do you think? Do we have to calculate that? It has 4 bonds to it. It has a 4 octet. No lone pairs.
0.
Yeah, it's going to be 0. What about this oxygen up here? What do you think? Got 2 lone pairs, and it's got
0.
it's 0. Good. Right. Anybody not following that? It's got 2 lone pairs. It's got 2 bonds to it. Right. And that's the ground state for oxygen. 2 sigma bonds and 2 lone pairs. If it has 1 bond, then it's going to be negative. If it has 1 bond and 3 lone pairs, then it's negative. If it has 2 bonds, I feel like I did this already, then it's neutral. And if it has 3 bonds to it, like the hydronium that we just looked at, I'm just going to use this as an example, and a lone pair, then it's positive. Those are the different cases for oxygen. So that oxygen down here, what do you think?
Is it -1?
-1. Excellent. -1. Good. So it's negative. What's the overall charge on that molecule?
0.
Let me zoom out. It is. It's neutral, isn't it? Because nitrogen is positive and oxygen is negative. Is that right? So
Yes.
the total charge on that molecule is going to be 0. All right. Any questions about that? All right. Let's go on to touch these dipoles again. We're going to start right here at the top of this sheet, and we're going to work our way through it. And then we are going to do some resonance examples, because I've sent you those resonance videos more than once, so you should have already seen them and have a basic idea of what we're going to be talking about. So I'm going to give you the introduction, and we're going to jump in and do some examples. All right, so let's go right here. Somebody whip out the trusty periodic table. tell me what the most electronegative atom is in this molecule. And why does electronegativity matters when we're talking about polarity?
It affects the dipole.
It affects the dipole. Excellent. Who was that? I can't see, but who was that speaking just now?
Justin Norwood.
Yeah, okay, good. Put your Cash App in the chat. Thank you for that answer. I'm buying you lunch today. So the electronegativity is going to dictate the dipole, is going to determine whether the dipole is towards one atom or towards the other. Is going to affect the polarity of the bond, and it also affects how it reacts, the reactivity, which we will talk about later. But again, I'm introducing you to topics as they come up, because why wait if you can get it now? All right, so out of all these atoms, right, we know these are all carbons, is that right?
Yes.
Yes.
Those are all carbons. What type of depiction is that? Is it a Lewis structure? Is it a condensed structure? Or is it a skeletal structure?
Skeletal.
Skeletal.
Good.
Skeletal.
Skeletal structure, right? So if I ask you what this carbon was right here, what would you say? There's a little lag between mine.
CH3.
It's a CH3. Excellent. What about this?
CH2.
CH2. What about this one? Again, I'm just bringing up old stuff to make sure you don't forget it.
CH3.
Not quite. Look at how many bonds that carbon already has.
CH.
It's a CH. Good. All right. So let's go and answer the question. What's the most electronegative atom in the compound below? What do you think? Look at the periodic table. Do y'all know the trend? Remember the trend from Chem part 1? It's increasing left to right.
Is it oxygen?
Oxygen.
Oxygen. Good. Increasing left to right, and then decreasing from top to bottom. Is that right?
Yes.
Right. That's the trend for electronegativity. You don't have to guess. If an atom is to the right of another atom, or if it's below it, it's going to have a lower electronegativity. All right. So in this case, oxygen is the most electronegative atom. All right. Let's go to the next question. Which of the following statements correctly describes the typical bonding of carbon, nitrogen, and oxygen in organic molecules? We just talked about that too. Which ones can you rule out? Right? Look at what it says. It says typical bonding. So that's under normal conditions with no charges or no special cases. It's typical. How many bonds does carbon typically form?
4.
4. So the answer is going to either be A, C, or E. Is that right? Because all of those have carbon participating in how many bonds?
4.
4. Right? So we can rule out B and D right away. Can't be that. Can't be that. Is that okay? Are y'all following the logic behind that?
Yes.
All right. Now let's look at the next statement. Let's go to let's look at A. It says carbon has 4, participates in 4, oxygen participates in 2, and nitrogen participates in 5. Which one of those is false? Remember, we just said nitrogen
Yeah.
in its typical state has 3 bonds to it and a lone pair. It can make 4 bonds and go hypervalent, but it can't make 5 bonds, because then it'll have 10 electrons around it and violate the octet rule, right? All right, let's look at C. Which one of those statements is false?
Oxygen.
Oxygen, right? So if we look at E, we see that carbon, and this is again foundational information. If you know this, then it makes it much easier to kind of move through other topics, right? So that particular set of answers says oxygen has 4 covalent bonds. I'm sorry, carbon has 4, oxygen has 2 covalent bonds, and then nitrogen has 3 covalent, and that is absolutely correct. A typical carbon is going to have 4 bonds to it and no charge. A typical oxygen is going to have 2 bonds to it and no charge. And a typical nitrogen is going to have 3 bonds to it, a lone pair, and no charge. All right. Let's go to the next. Any questions about that? Go ahead. All right, let's go back to number 3 of the molecules listed. Which one does not have a dipole moment? How do we answer that question? What do we need to know about dipole moments to answer that question?
Can you say the answer for the last question really quick?
It's E.
Okay, thank you.
All right. Of the molecules listed, which one does not have a dipole moment? How do we know which one will have one and which one won't? A molecule now, not a bond, a simple covalent bond, but an actual molecule. Because remember, you can have multiple dipoles, but they may either cancel each other out or they may not be large enough to create a molecular dipole. So how can we tell that?
To know the electronegativity.
Know the electronegativities, and then there's one other thing that we need to know too. What is that?
The Lewis structure.
Yeah, because if it's symmetrical and somehow the dipoles cancel each other out, that's a problem, right? That'll create a situation where there's no dipole possible, right? So you're going to look for symmetry. And then you're also going to look for whether or not dipoles are going to cancel. So if we write out CO2, it looks like this. Where it's all neutral, but, and then we write BF3, it's going to look like this, B. All right. What do you think? Which one is not going to have a dipole?
C.
The CO2, very good, right? It's symmetrical and the dipoles are going to cancel, right? If I look at BF3, all of these dipoles are moving in the same direction towards fluorine. So that's going to put a huge partial positive on boron, right? And we can take all those vectors, since they have the same general direction, you can take them and add them all up. Got a big molecular dipole going this way. Remember the arrow tip, the arrowhead is going to be negative, partially negative, and then the arrow end is going to be partially positive. All right. So these are going to cancel. All right. All right. Can you see how HCl will have a dipole towards chlorine?
Yes.
What about the NBr3? Let's talk about that for 1 second. Which of the 2 atoms are more electronegative? Look at the periodic table. Which one is furthest to the left?
Nitrogen.
Nitrogen. Look it up. Somebody Google the electronegativity of nitrogen.
It's around like
Say it.
3.04.
3.04. And what about bromine?
2.96.
2.9. You see that? So it's all this is verifiable, and it's going to follow the trend of left to right, top to bottom, increasing from left to right, decreasing from top to bottom. So which way is the dipole going here? In each bond?
Up.
Up towards nitrogen, isn't it? And then that lone pair is in a p orbital. Let me fix that. Just make that small. That lone pair is in a p orbital. And that is, those electrons are going to be tend to move away from that atom. So it's going to have a big dipole going this way, right? Overall, like, again, a dipole moment is how we describe molecular dipoles. All right, we okay so far? Everybody straight?
Yes.
All right, let's do this for this question. Let's look up the electronegativity values for rubidium, fluorine, oxygen. We know fluorine is 4.0. That's the most electronegative atom on the periodic table. And then we know oxygen is 3.5. So we just need somebody to look up rubidium.
0.82.
0.82. Highly, highly, highly not electronegative. All right, so if I ask you to list in order of increasing electronegativity, which one would be first?
Rubidium.
Rubidium will be first because we're going from least to most if it says increasing. So rubidium will be less than oxygen, will be less than fluorine. Is that right?
Yes.
All right, so question is, which answer is correct? Do we have that answer listed?
No.
No, we do not. All right, so that answer is not available to us. All right, let's go to the next one. What's the definition of a polar covalent bond? Equal electronegativity between the atoms, slightly different or greatly different. What's the scale? Can anybody remember what the scale is that we talked about on Wednesday?
Wasn't it from like 0.4 to 1.5?
Yes, for a polar covalent, and 0 to 0.3 for a non-polar covalent. So it's going to be A, am I right?
Yeah.
All right, good. I want you to finish this back page on your own. All these are very simple examples where you pick where you just pick the right dipole arrow. All right, now we got to jump into resonance. So I'm gonna add another page, and this will be the last thing that we talk about today. So resonance is kind of like, it's a couple. There's a couple of concepts that we need to talk about. All right, there's a couple of concepts that we need to talk about. So first thing is, I'm gonna draw a functional group. So let's say C. Let's draw the Lewis form for this, Lewis structure. And carbon is my central atom. All right, so I'm gonna put a carbon here. No, sorry. I put a carbon here, and it's got 4 valence electrons. Is that right?
Yes.
I'm gonna put this carbon here. I'm just gonna leave it as a CH3 because we know that that's one functional group. It's a methyl group. And then we have an oxygen here. Let me move this. All right, we got an oxygen here. How many electrons around that oxygen? So valence is 6, right? Is that right?
Yes.
All right. So here, if we look at the carbon, right, we have 4 bonds around, 4 electrons around it. I need to put an H over here. Sorry. Right. So we're gonna put the H out here. So now this carbon has 1, 2, 3, 4, 5, 6, 7 electrons around it. So it doesn't have an octet. And so the way I fill out that octet is I can take another electron from oxygen and move it here. Right, and then I can take this electron and move it here, right? And so what that creates is a pi bond or double bond between carbon and oxygen. So the line form for that would look like this: H, C, and then double bond O, and then CH3. Right, but I can write another representation of this through what we call resonance. I could take that pair of electrons in that pi bond and shift it using a curved arrow up onto oxygen. So I can also write a form of this that looks like this, where oxygen has now 3 lone pairs and a minus charge, and then the carbon has a plus charge. Right, and I can write it like that. So one of the first ideas or the first concepts tied to resonance is, to be able to show the different depictions of a Lewis form. Not are, but can be. Right, how Lewis forms can be depicted. Right, so the form that actually exists in the universe is kind of like a mix between the left and the right. So we call it a hybrid, but we normally show it as this structure right here because it's neutral, there are no charges, and it's stable, right? But the actual form that exists is a cross between those two, and we call that a resonance hybrid. So let me write that in here. So that's a cross between, that's shorthand, all resonance forms. All right, so it's a cross between resonance forms. All right. So another aspect of resonance is that we think about is not just depicting Lewis structures, but also stability. Right. So resonance as a noun is a depiction, but resonance as a verb is delocalizing or moving electrons around to make a molecule more stable. So I'm gonna show you that too. So you're gonna hear this term stability thrown around a lot. And what it literally means is that when we're doing anything in chemistry, it's always gonna come down to how stable or unstable something is, right? More stable is good, less stable is bad. It's that simple. But let me show you an example of why this matters. So I'm going to show you 3 different scenarios. I'm going to show you, and these are patterns that you can look for when you're trying to figure out whether or not a molecule can do resonance, right? You can look for these patterns. If you see them, then you know that resonance is possible. This is what we call an allylic anion. All right, you got 3 atoms. I'm sorry, yeah, allylic, it's an anion. You got 3 atoms and the carbon is negative on the end. The allylic, this is the allylic carbon right here. The one that's adjacent to the pi bond. That's all that term allylic means, that you have an atom that's connected to a pi bond or a pi system. So the definition of allylic is an atom that is adjacent to a pi system. So you got an allylic anion. You can also have an allylic cation. Oh, too light, sorry. Do you see how, and let me put there's a hydrogen here, by the way. I just didn't draw it in. But do you see how formal charge and all this stuff is kind of tying right back in? All right, so that's an allylic cation. It's a cation because it's positive. And then the other pattern that you can look for is an allylic radical. And we're going to talk a lot about radicals later on. So it's going to be the same structure, but the allylic part is going to be slightly different. It's going to have 1 electron. Right, so a radical, let me give you the definition of that. It's an atom. Jumping the gun. So it's an atom with an unpaired electron, a single unpaired electron. All right. Single unpaired electron. So with resonance, all 3 of these can do resonance because there are 2 things that have to happen, or 2 things that have to be present. You need a donor and you need an acceptor, and they got to be adjacent. Right, so your donor, an example of a donor is a lone pair or a pi bond. Example of an acceptor, a pi bond, or a cation. Those are your donors and acceptors. When we talk about donor, we're talking about donating electrons. So it can either donate electrons or accept electrons. All right. So we have 3 scenarios that we can look out for. We got a allylic radical, a allylic cation, and an allylic anion. And resonance happens in 99% of the cases where resonance happens, it happens for the purpose of stability. Because one of the things about, like, if we look at the anion, and we're going to stop right here, that pair of electrons on carbon is not stable just sitting there. So carbon wants to share those electrons with the atoms close to it. That's why the acceptor needs to be adjacent to the donor so it can take those electrons. And as a side note, the way that you share electrons, how do you share electrons with other atoms? What has to happen?
You can form another bond.
You can form another bond, true. But how do you form that bond? What has to happen between the atoms in order for you to share electrons?
Orbital overlap.
Orbital overlap. Orbital overlap. So that's why the donor and acceptor have to be next door to one another. If there was 1 atom extra between that negative charge and that pi bond, there was another carbon in there, there could be no orbital overlap and you cannot do resonance. That's a key, really a key concept. In order to do resonance, you got to have your donor and your acceptor next door to one another. If not, they can't overlap orbitals and they can't share electrons. All right, so we're gonna pick this up Monday, and then we're gonna work it in around the other concepts that we're talking about with the solubility and intermolecular forces and all that stuff. We're gonna work all of that in, but we'll pick it up on Monday. All right, so if you need to go back and watch those resonance videos again, do so, because this right here is one of those things that'll cripple you going forward if you don't get it. So you got to get it, and if you don't understand it, then you got to let me know where the gaps are so I can help you fill them in. All right, but this is I was doing a study session last night with my 9 o'clock class, and all the questions centered around resonance because nobody remember how to do it from part 1. So this is a skill that you need in your toolbox from this point all the way through the second part of organic. You got to have this. If you don't take nothing else, you need to know how to calculate formal charge, how to do resonance, and then how to identify what if a carbon is partially positive or partially negative, because all those 3 things dictate reactivity. All right, so we're going to stop right here. We're going to pick this up on Monday. Make sure that you watch the video.